So, hi everyone, and thanks for coming today evening. I'm going to talk about deep reinforcement learning in medical imaging. 10 years ago, I was a young boy, around 15 years old, and I used to go to school. And I'm from India, so every time I went to school, I had to give some sort of tests, and my aim was always to score the highest possible score, 100 out of 100. Every time I got this test back, I get something wrong, of course, and the teacher would write a note, get test signed, do corrections. Why should I do corrections? I thought, I've got it wrong. But my aim was to score the highest possible grade, and I found that doing these corrections repeatedly made me learn the answers better. And therefore, when I was faced with new problems, which I hadn't seen before, I was able to answer them. I was learning from my past experiences. Ladies and gentlemen, this is called reinforcement learning. More mathematically, reinforcement learning is when an agent has an environment. The environment exists in a particular state, and to improve the state, to go to a better state, the agent makes an action. Now, how does one know that this action is better or worse, or whether the state achieved is better or worse? Well, a reward is calculated, which was achieved by changing the two states. The job of this agent is to find the best possible rewards and therefore find the best policy to achieve the greatest possible states. Deep reinforcement learning, though, is what I'm talking about. Now, when people think of agents, the greatest agents possible are Agent Smith and Agent James Bond. They're not suitable for this task. A good agent we use is called a convolutional neural network. A little bit of explanation for people who are not studying machine learning. A convolutional neural network is a technique which makes a weighted sum of all the pixels in your image. This weighted sum is calculated, and then the outputs are compared to some ground truth, some answers which we already know. Depending on how bad the errors are, we go back through our network step by step and see what the weights of our weighted sum are and change them. And this process goes on ad infinitum, or in reality, till a certain amount of time. Some mathematics, I won't go too deep into this. The perfect action Q is achieved by a sum of the reward and the discounted sum of the perfect action at the next state. Now, there's a really complex derivation, and I won't get into it right now because this is just a small presentation and not a mathematics lecture. But let me just point out, in real life, nothing is perfect. So we don't have a perfect Q. This equation doesn't always add up. What that means is we take this equation and we can find out how much it diverges from a perfect value. Now we have our errors, something which we can reduce, something which we can use to update our weights, as I showed in the previous slide. But this has been involved for specific tasks. And the first task was by the great, of course, Google on video games. And let me just try to show you this quickly. Well, the next task it was designed for was Go, a 1,000-year-old game from South Korea. This algorithm was trained and played against the best Go player in the world, Lee Sedol. He predicted a 4-1 scoreline with which he would beat the algorithm. He got the scoreline right, he got the winner wrong. And I won't tell you much in this detail, but there's an amazing documentary which you guys can check out on YouTube. It's not very technical and it's very fun to watch. But we are the health hackers, not just the hackers. So let's talk about medical imaging. This happened this year where someone used deep reinforcement learning for active learning. Now, how this paper worked is that usually you want to classify medical images, but doctors don't have the time to sit and label medical images, especially during a pandemic. They've got better things to do with their time. So with a small amount of labeled data, an annotator was put and he was given images to classify, a small number at a time, maybe 5 to 7. This was put in and the result was found out for the automatic classifier. Now, the ones which were misclassified more strongly were put back into the training set again and again. And choosing these samples was the job of the actor. And using this actually improved the performance of the classifier a lot more. We have now this paper from MIT. They want to use deep reinforcement learning on MRI volumes. They want to find the pose estimation of a fetus in the womb. And they use a deep neural network to find many different landmarks which can be used to estimate the pose of the patient. So I'm not an MR expert, but I think this was pretty cool. Another pretty cool paper by the greatest medical imaging company ever, Facebook, because why not, was not based on speeding up MRI sampling. The ones on the left are MRIs acquired at 2 times the normal speed, and on the right are MRIs acquired at 3 times the normal speed. And they actually managed to increase the speed by a significant amount while maintaining image quality. Now, these are a lot of works in the medical imaging area, but I didn't do these works, so I can't tell you all the details about it. Let me talk a little bit about my work on low-dose CT. So why do we need anything? Look at these images. On the left, you have a full-dose image. On the right, you have a low-dose image. As you can see in the zoomed-up areas, some of these small features are just gone. They're destroyed by noise. Let's go back a bit. CT is a pretty important tool in diagnostic and interventional procedures, but it's really radiative. It's like 40,000 chest X-rays or several thousand bananas. And in fact, it's important for causing a lot of cancers. Estimating 1 to 2% are caused due to CT radiation. This is a significant problem. And this is why, to increase the safety of the patient, we keep trying to reduce the dose as much as possible. It's called ALARA, as low as reasonably achievable. But that creates noise, as you've seen, which can destroy image features. And in fact, the most important features lost are these small low contrast tumors. And therefore, we want to try to remove them as much as possible. Usually, they use some non-linear filtering approaches, just normal filtering. But modern scanners have a lot more computational power. So they use iterative reconstruction, where you have the sinograms, X-rays collected by the scanners. You do some reconstruction to make it a CT volume, compare it to the collected projections ad infinitum until you start to get a good looking image. And this actually exists in the latest scanners from everybody. However, the most experimental techniques are by Canon and GE. They've gotten deep learning in their scanners. How does it work? Well, nobody knows. That's why it's in their scanners. And usually people use deep learning. They think of it in terms of what Facebook or Google does, where you put one image in, you get another image out. And there's many different models. I won't go into the details of that. But the main problem in deep learning is that you have this magic black box with, I don't know, 100 million parameters. So even if you train it as much as possible, all you can say is that, yeah, empirically it works. And that doesn't cut it when it comes for medical imaging. You need much thorough, much more advanced testing. So In our work, instead of trying to just go from noisy to clean, we try to learn how to remove noise. We use a filter called the joint bilateral filter. And for the joint bilateral filter, we have a guidance image for which we use a magic black box. I'll agree to that. And then we have these small hand-tuned parameters within the filter. And these are the parameters that we train using reinforcement learning. So let's go bit by bit. This first is a structure. We have our image, we get a prior image, we have the bilateral filters, we have two parameters whose value is tuned by parameter optimization network. And then based on how good it is, we estimate the quality with the quality CNN, and then we put it back in and repeat the process until our network is clean enough. In practice, usually one iteration is enough to remove all the noise. A little bit in detail, let's go into it. Denoiser network. So it's networks with convolutions, and each convolution is a 3x3x3 kernel which slides over the entire CT volume, calculating the weighted sum. We actually use residual networks. So for example, each convolution loses some information. We take some of the lost information and we add it back in later layers. And we found that this actually improves the quality of the image quite a lot. The nice thing is we only need 10 patients, whereas the approach I showed you before from MIT and Facebook needed a lot more. I think almost 600 patients. The quality CNN, yeah, it's just straightforward. You take a bunch of weighted sums, go deeper and deeper, and output a number. And here's the nice part, the parameter tuning network. We have 2 sigma parameters in a bilateral filter. So what we do is we choose one of them, and then we choose how much to change it. We see what the image looks like. Based on what the image looks like, we choose another parameter, or maybe the same one. We tune it more, and then we see again what the image looks like, which is exactly how a human would do it. We just have the network taking the place of a human. How does this work? Does it work well? Well, I'll show you one of our sample images. On the left, you have your low dose noisy CT, and on the extreme right, you have your clean CT. And as we can see, our method, which is the second on the right, gives us the closest result to a standard dose CT. Just using a filter and not doing the parameter changes will remove everything. So that makes it a bit too clean. Whereas not using our quality network to estimate quality and using mean squared error or a more simple comparison method just makes it more noisy actually if you look at this sample. Qualitatively, we have our method and we compare it to most state-of-the-art methods. And we find that ours preserves the most structures. SSIM is your structural similarity, how many structures are present still. We find that when we compare ours to the clean image, we have the most number of visible structures. And yeah, we don't remove the most noise, but what's more important in medical imaging is to make structures more clearly visible rather than just removing noise. I mean, to be frank, you could just take a completely black image with zero noise and then you've succeeded as well. And in the end, we developed a method to denoise low-dose CT scans while preserving the features. And this method has better results than our deep learning networks, which have, as I told you, hundreds of millions of parameters in many cases. And the nice thing is that we can interpret how this method works. You know, at each point that is just doing a filtering, we know how this filter works. We have several years of experience. And we still get to use the power of machine learning, in our case, reinforcement learning, to supercharge our filter to get the best denoising results. And some future possibilities of our work is just based on the physics of the CT mostly, actually, because the reinforcement learning task here is pretty simple and it works pretty quickly. So thank you. And I'm done with my presentation, but if any of you want more details on my work, I have this link which is present in this slide, which I'll also share in the chat, which will give you an idea of our work, and it's present on my website, which you can interact with. So thanks, and I'm happy to take questions now.
Thank you, Mayank. I will stop the recording now.